Actually, we have learned this page last time. Do you guys still remember? Do you guys still have some impression? So let's review that. How should we do that? So actually, we try to move out the forces from its original acting point, maybe here, maybe there, moving into the common point O. Then, according to the theorem of translation of a force, we translate every force to the point O, right? Actually, according to this theorem of translation of a force, we know when we translate a given force from its original point to this new point O, we should add a couple, right? Actually, this couple is the original force, is moment to the point. So let us select F1 to be an example, and we review that together. See, if F1, this force originally acting on this point on this object, then we want to move this F1 from here to here. So we should first do this calculation. Actually is MOF1, right? Actually, it equals R1 vector cross products F1 vector, right? So we can call that equal M1 just to be equal to this one, right? So we can just move this F1 from here to here. When we do this so-called translation, we should keep its magnitude and direction be the same. So it's just another force F1 prime have the same direction and same magnitude, but we should add this M1, right? That is all the theorem of translation of a force about, right? Actually, we can repeat the precise. So we can from F1, F2, until to Fn to move all the force into a same point, right? Then we can get a concurrent force system. So in China, we call that 空间汇交力学. That means all the forces in this system have a common point here. So we call that concurrent force system in space, F1 prime, F2 prime, F3 prime, until the last one, Fn prime, right? Because according to the theorem of translation of a force, we add from M1, M2, until to Mn. We call that a couple system of transfer. Actually, we can call that 平移力有律, right? We can call that 平移力有律. 平移力有律. A couple system of transfer. Is 平移力有律系统 right? And 空间汇交力学 actually concurrent force system in space means 空间汇交力学. Maybe you guys feel it's very difficult, it's hard for you guys to understand, but I only need you guys have a basic knowledge point and has a basic impression is enough. So don't worry about that. Actually, when we do the actual engineering problem, almost 95% the problem will be plano concurrent, in plane, maybe plane, right? So actually, its equation will quite simple compared to the results we discussed today, right? So don't be worried about that. You only need to listen to me carefully, understand as more as you can, right? So actually, when we use this theorem of translation of force, we can get actually, it means the original force system in space actually its effect to the body have the same effect. It has the same effect with this concurrent force system plus a couple of transfer, right? So actually, this is the medium term. Actually, the final result will be this because we know the whatever the number of this concurrent force system is, we can finally find use just R prime to denote this. Actually, this R prime is the reluctant force of this concurrent force system in space, right? And we also have another M0. We call this MO, not there. MO is the reluctant couple of this couple system of transfer. So compared to the original one, after this reduction, we will find actually this is very, very easy. Just a principal vector R prime and a principal couple MO, right? So in the third section of this chapter, we'll talk about the result R prime and M0 at different conditions. This object our rigid body will in a different state, right? So let's continue. So the second, because the couple in space is a free vector, it can always translate it to a point O. That means, so how you guys understand this second, that means if the original force system not only have n number of forces, but also have some direction of maybe couples, right? We call that M1 maybe. So actually when we use our right hand to find, actually this M1 will denote some given direction of vector. We call that vector of a couple, right? Maybe we also have this direction, we give it denote M second. So if the original force system have some couples, we only need to move into the same point. Because actually we mentioned the three factors of a couple is magnitude, direction, and action plane. So we can think about that if we can select a lot of plane which is parallel one to each other. So when we move this couple from one plane to another plane, it will not change the effect of this couple to the object. So actually the couple in space is a free vector is the reason. It can be always translated to the point O without adding any other things. That is a big difference from when we try to move a force. Can you understand that, my friend? So that's the big difference from when we move a couple like F1, F second to this point. We do not without adding any other thing. But when we try to move a force from its original point here to a point O, we should always give or add a couple, which is the moment of this force to this point O. That's the main difference, right? And composing F1 prime, F second prime, until Fn prime, we get the principal vector R prime. In other words, actually, we have this expression, Actually, this is how we do the calculation to find the reluctant force of a concurrent force system in space, right? It's very easy. It just means R equals sigma or sigma Fi prime, right? It's very easy. Actually, this is the vector equation. It can be projected onto three axes like x, y, and z. So actually, it means three scalar equations. We'll talk about that at the third section of this chapter. And the principal vector R prime passes point O, and it does not depend on the position of a point O. That means you can select, because this point O is arbitrarily selected by us. Actually, maybe we can select any other point like O prime, O double prime, whatever you like, right? It will not change the reluctant force of this R prime, because the principal vector R prime, it does not depend on the position of the point O you just select, right? In Chinese, actually, we see that 空间立交汇交力系的合力和我们选择的简化中心没有关系。That means it does not depend on the position of point O, right? So let's continue. And composing M1, M2, Mn, that's all ideal couples, because when we move one force, we should give one or add a couple at M1, right? So the resultant couple of these N couples, we get the principal moment MO. In China, we call that 主句. And R prime, we call that 主使, right? This is 主句, principal moment. And we call that R prime, principal vector. We call that 主使. So actually, you guys can think about that. Is this principal vector R prime, it will try to force this body to move along three directions of X, Y, and Z. And because of the principal moment MO, it will try to let this object have some rotation around X, Y, and Z. Actually, maybe it just try to force this body rotate around the arbitrary axis, but that axis also a vector. It can have three components along X, Y, and Z. That's why we always said a free body in space will have 6 freedom. 3 of translational movement and 3 of relational rotational movement, right? Actually, we have mentioned that a lot of times, many times, right? So it tells us MO actually equal this. So the principal moment MO depends on the position of point O. That is another big difference from MO, the principal moment, to principal vector R prime, right? So we have the same original force system. If we select a different point O prime, maybe MO prime do not equal to M0, but M prime, that this is O, another R prime, that is O prime, will always be the same, with the same direction, with the same magnitude, because it doesn't depend on the position you select. That's the principal vector, and this is the principal moment, right? So I hope you guys have a basic knowledge about that. And after we review that, we can think about, let's the center O be the origin of the coordinate system, like X, Y, Z. Then the magnitude of principal vector, we have R prime, the principal vector, equals sigma Fi vector. At this side, it is the vector equation, so it can be projected onto 3 axes. So we have this. So actually, this 3 equation means our principal vector R prime, this is the arrow to denote that this is the vector, equals Rx prime, which this one is the scalar, because this I prime, this I means a uniform direction along x positive direction, right? Plus ry prime g direction and rz prime k direction. So actually this means the principal vector, it will have three components. One is this, another is this, and another is this. So actually this sigma x, you can maybe this write at this, you guess will more easily to understand, right? I from 1 to n is number of this random force system. So each force is a vector, right? It also have a component along x. So the whole sum of all these forces component along x will be Rx prime. No? So after we do that, actually this is just a average vector in space. So we can use, we have learned mathematical knowledge to find a magnitude. Magnitude of the principal force or principal vector. Actually, this is 向量的模, right? Or 矢量的模, norm of an vector, VECTOR. So whatever the vector is like, it just has three components. So we can use this equation, squared, this one squared plus this one squared plus this one squared, right? So that's how we can find magnitude of the principal vector of principal force, right? And another is how to find its direction. Actually, that is very easy. As long as we have this, it's very easy, right? Very easy. So I can just erase this line. So maybe something will show here, right? And so you see, this cosine r prime f. This means we just consider the direction of this r prime. It intersects the angle between its direction and x, its direction and y, and its direction and z, right? So if you have this value, you can use anti-cosine to find its given degree, right? That's easy. You just need a calculator or software. Is enough. See? So let's continue. And according to the relationship between the moment of a force about a point O and the moment of the same force about an axis through the point. So actually, we have repeated that many times. So maybe I can repeat that just one more time today. Actually, if we have this, actually MOF, we can write like this. MOF is just a force. We just consider its moment to a point. Actually, this one will be a vector, right? So it may be, I can write like this, mx I direction and my g direction plus mz k direction. How can we get this result? Actually, we only need to do the calculation of determinants I, j, k, and this x, y, z will be coordinates of its persistent vector r, and fx, fy, and fz, right? And what about the relationship? Actually, we can interestingly find actually this component actually it has the same force its moment to axis x, right? And actually this component along y direction of MOF, actually it is the same force its moment to y axis. And MZ actually will be the moment of the same force F to Z axis. So that is a very important relationship between the moment of a force about a point and the moment of the force about an axis through the point, right? So in some cases, if you can use this relationship, you can simple your calculation. And the principle or the magnitude of the principal moment will be this. Actually, it's just another vector, right? It's seen from the principal force or principal vector, right? It's just another vector, right? So I think you can totally understand that. It just need you have some basic mathematical knowledge, right? So let's continue. Actually, I think we stopped here last time, right? So we can once again think about the fixed support. It's very common used a kind of constraint. So I think I have mentioned that there are 5 common type of constraints that you guys should know and know each kind of constraint how to give its reactions, right? And see, actually, this is the fixed support. Fixed means this bar cannot move. It will have zero freedom. It cannot move. It cannot rotate, right? So consider the force Fi acting in the same plane. Actually, this is a fixed support in plane, right? That means this bar firstly should keep on this screen, this is the plane, and secondly, it fixed on this plane. So do you guys still remember we always said a free body in plane will have 3 freedom, right? 2 of them are movement along x-axis or along y-axis. The third one will be around some axis which is perpendicular to this plane as rotation, right? So this means if this is a fixed support just in plane, right? And then all the 3 freedom will be prohibited, will be constrained, right? So this bar cannot move a little bit. Then actually we can think if it fixed into a wall, there are a lot of force which are trying to prevent this bar from moving in some matter, right? So we can use the reduction method. So just reduction this whole force system into point A. Then finally, we will get a principal vector RA and the principal moment MA, right? So reduce all the Fi to point A, get a force. A force means principal vector and the couple, right? The direction of RA is uncertain. We don't know what its specific direction should be. Then we can just use 2 components, 2 rectangular components, YA and XA, to denote its direction, right? Because RA always equal XAI plus YAG because it is in plane, so it always have 0 components along K, the direction, right? So that's why you guys should remember a fixed support in plane, its reaction should be 3 and in this form. So X A Y A M A. That's why the reaction should be this. So you guys also can consider from this point of view. Actually, its reaction is trying to prevent each capable of movement from happening. I always see that, right? So YA, XA, and MA are the reaction forces of the fixed support, and YA and XA, right? YA and XA restrict the translation of the rigid body, and MA, right? For the consistent restricted rotation. So it just help us to understand why this fixed support in plane has three reactions from what we have learned, just learned a force system reduction, right? So let's continue. So we are going to move to third section. So maybe I should mention that actually you guys may find this section is very difficult to understand because actually we talk about the force system in space. But please, you guys don't be worried and don't worry about that because after the discussion of this section, our example and our common engineering problem we encounter in future, maybe will always, or 95% will be a force system, not in space, in plane, right? So you will find actually if a force system is plane, the equation will reduce from 6 into just 3, and it's quite easy to understand. So please, you guys just listen to me and try your best to understand. If you cannot, it's okay. It's okay. Don't worry about that, right? So I will continue to talk about the discussion of the result of the reduction of a force system in space. So if a force system in space is reduced to a given point, like this figure, we get resultant force R prime, which we call 主使, right? Principal vector in Chinese call that 主使. And a resultant couple MO, we call that principal moment in Chinese, 主句. So this kind of principal vector will try to let the body to move along some direction. And this resultant couple MO will try to force this body to rotate around some axis. So since we have R prime and MO prime two vectors, so it will have some kind of we should discuss from. So the first we'll talk about if when we finish our reduction, we find R prime equals 0, MO equals 0. So what that means actually is the best result we want to encounter. Why? So if R prime equals 0, MO equals 0, it means the force system is in equilibrium. So the body in the state of balanced, balanced. In Chinese, we call that 平衡, right? 平衡. So if we are lucky, when we finish our reduction of force system in a general force system in space, we finally find R prime equals 0, MO equals 0. That means you can arbitrarily select different point, whatever you like. Which point you like, you will always find R prime equals 0, MO equals 0. Why? Because the force system is in equilibrium. So whichever point you select, it always will be the same result. 它是平衡的, right? So the second is if R prime equals 0, MO not 0, it's not 0. So what that means? So this is the category the second situation. So if R prime equals 0 vector, right? It's 0 vector. So because this R prime is it does not depend the position you select. So that means the original force system is equivalent to MO. See? Can you guys remember? But I think, can you guys understand that? That means the original force system, its effect just is equivalent to this MO. Although we always say that this MO is the principal moment, it depends on different position or of the select point, right? But under this condition, if R prime equals 0, that means the original force system is equivalent to this MO. That means you can arbitrarily select any other point. You will find actually MO prime equal MO double prime equal MO. Why? Because under this condition, the original force system is effect to the body just equivalent to this M, right? And actually a couple is 3 factors, just magnitude, direction, and action plane. So it doesn't depend the position it actually acting on, right? So you will find this. So the moment is equal to the sum of moments MO of the force about a given point. The principal moment does not depend on the position of the given center. That's why. Why, if R prime equals 0, MO does not equal 0, the principal moment does not depend on the position of a given center. Why? Why this is true? Because this time, under this condition, the original force system is equivalent to a couple, right? So all the couple will be the same, have same magnitude, have same direction, and have same action plane. See? I hope you guys can totally understand. If you cannot, that's okay. That's okay. Just try is enough, right? So let's move to the third category. If R prime not 0, but MO equals 0. So that means, so this condition means because R prime not 0, right? And the force system is equivalent to a resultant force. So I can draw a body just like a potato here. So whatever the original force system is, so maybe we just select this point O, we find actually the original force system is equivalent to just a force R prime. You know, under the rigid body assumption, because we have talked about that through the from the very beginning of our course this semester. So what is rigid body? A rigid body means any load or any force or couple acting on this body, it will have not any deformation, right? So we have the principle. This R prime can freely move along its action line without changing its effect to the body, right? It means actually if we just under this condition, we can freely select different point or prime or double prime or triple prime and a lot of points. As long as the point is on the action line of R prime, we will always have the same result. So in other words, that means the reluctant force of this force system will through this point O. So let's see, it tells us the principal vector. The principal vector R prime, which is equal to the resultant force vector R of the force system. So the principal vector R passes the given center. Why? Because the original force system is equivalent to a single resultant force R prime. And according to the principle of theorem we have learned, actually because under the rigid body assumption of this object, so a force can freely move along its action line without changing its effect to the body. So that means the reluctant force of this original force system will through this point O, right? So it has it depends on the position of the given center. If the point O is changed, the principal moment is not zero. So that means, let me explain this sentence again. If you select a point, let's say that A, and this point A do not on the action line of R prime, then we can, according the theorem of force translation, we can translation this R prime to here. We denote it with R double prime. And we also should add a couple, which means it equal to R prime to this point O. So this M will equal MA R prime. So this couple plus this R double will equivalent to this R prime. That means if you select the point which is on the action line of R prime, you will always get the same result R prime. But if you select the point do not on this line, then it moment MA will do not equal zero, right? Can you understand that? I think maybe it is hard for you guys to understand. But actually, we just use what we have learned, theorem of force translation, and actually under the rigid body assumption, a force can freely move along its action line. All these principles we have learned from the first and second class of this semester, right? So this is the third category, 第三种情况. So we'll continue to talk about that. So actually this one may be is a very general result. So after the reduction, we find R prime not equal zero and MO not equal zero. So there are three kind of situations separately. This is very complex, right? So please, you guys just listen to me and try your best to understand. You can maybe you guys, teacher Fang, I totally have no idea what are you talking about. Don't worry, it's fine, right? It's fine because it is a force system in space. It's quite difficult, right? It's difficult for my Chinese student, and I teach you guys in English because my English is that good. So I hope you guys can understand a little bit, right? So if R prime not zero and MO not zero, there are three kind of situations separately. The first is if F prime perpendicular to M0. Actually, it is a plane. So let's say this original point O, we have R prime. Thank you, number 10. Okay, so we also have MO here. So we find actually this MO is on this plane, and this R prime is on this plane. So we can think about, we can just move this R prime to different point. I think it's quite difficult to understand. Maybe I can draw a picture here. So this time, I will draw that. Maybe we can have a R prime here, and we have a MO here. So this is point O, So this time I will change the color of my pen. So actually, this plane also is the action plane of this couple MO and it up prime. So if we use our right hand rule, we can just let our 4 fingers folding along the direction of MO here. We will find actually this MO, it also can be denoted as a vector direction up here. So actually this is the MO. Right? This means if you look at this plane from this point downward to this plane, so you will find that the effect of this MO will try to let this object rotate around this axis, right? So if we just look at downward to this, if this is the CCW direction, you know what is CCW? Counterclockwise, counterclockwise. So you will find it try to make the object to rotate around this direction. So actually this is R prime perpendicular to MO because we use this vector direction to denote the direction of a couple. So that means we can do this. You see, I think this will let you get very easy to understand. So we can arbitrarily find another point like A, maybe A here. So you see, we can just use the theorem of false translation, right? We can move this R prime to here by keep its magnitude and direction R prime. And we also should add a couple, right? Add a couple M, which should equal sigma, we do not need sigma, which should equal to MA R prime, right? That means the moment of this R prime to this A. So we can see actually there have some distance from, if I draw an aided perpendicular line, which is hard to draw, which is perpendicular to the action line of R prime, because that's D. Actually, this odd couple M should equal magnitude of R times its distance D, right? So actually, this is CW direction, which is clockwise direction. So because this M0, it can freely move from this point O to this A. So once again, I will change the color. Maybe we use what green. So we can just freely move M0 here, MO here. So you will find actually at the new point A, we have R prime, and the new MA will equal M plus MO. But actually these two guys have different position, different direction. So actually we can use that MO minus M. So we are trying to get this result will be 0. So that means we only need to let this R prime times D equal MO is enough, right? That means you should find D equal R prime. That's why. So that means actually this figure is very easy to understand compared to this one. That means the first condition is if R prime and MO both are not zero, and plus the subcondition R prime perpendicular to MO, then we can find another point. And like the resultant force of the original force system just only have this R prime. You see, because actually this M, if we select appropriate balance this MO, right? So that means actually our final results can be further reduced to just have R double prime, right? But it's not the original, its action line will not through this O, but will through this point A, right? So can you guys understand that? So that's the result. That means turn MO into R prime and R, where R prime counteracts R double. So we get R. Then what's the result? Actually, we can find the new R. It will just through this O prime. And this O prime is distant from the original point O, will have the reason I write here by my pen, right? I think it's very hard for you guys to understand, but please try your hard, try your best to just have basic impression, okay? So the second subcondition is this time R prime parallel, not perpendicular to M0. Then we don't have any measures to counterpart this MO. So we call it wrench. So it's more like a wrench. Actually, in Chinese, we call that 利螺旋. So you guys can think about helicopter, you know, 利螺旋. So what is wrench? Maybe it is a tool, right? That means it can rotate around some axis and at the same time it move along this direction, right? So just think about helicopter. Do you guys know helicopter? Helicopter have maybe this one very fast. So I don't have the gift to draw a very beautiful helicopter, but that mean. So maybe they have some window. So maybe you guys will have money to buy your helicopter, right? Am I just drawing a helicopter, right? So because this one needs to rotate very speedy, and then this one can counterbalance the force, gravitational force, and then 升空, right? Lifted. So we call this situation is 力螺旋. And there another example, we operate a screwdriver, you know, maybe we have a part and it have a very polished hole, then we can use this screwdriver and let it have internal screw. You know, 内螺纹, right? 内螺纹, screw. We call that screwdriver. And in China, we call that 板牙, right? So that means it will move along this direction, also rotate. You can also think of a bullet from a pistol, very speedy from this point to another object. So the speedy will more like this. It will move along this direction with high speed rotation movement, right? So I think it is a time for us to have a short break. We'll restart at 11:10. Okay, so you guys have rest.
خلاص.
Okay.
We can't see.
Okay. Okay, well, I will continue to my lecture. Maybe I cannot record the second class today. I don't know why, because I cannot find that menu just put down the record button. I cannot find that. So maybe I will not record the second class today. So actually, this is very important subcondition collinear force couple system called the range. Actually, in China, we call that 力螺旋. You guys only need a basic impression is enough. So let's continue to talk about that. So R prime and MO are not perpendicular to each other. That is a very generalized situation, right? So also under the first condition is R prime not zero and MO not zero. But this time R prime and M zero are not perpendicular to each other, also not parallel to each other, right? So actually you guys can see at this time we just need to do a decompose precise. We can have two component of MO. The first one is M parallel, which M parallel is parallel to this R prime. Another is M perpendicular, which is on the plane. This is perpendicular to the plane. So actually, that means the two cases we just finished discussion, right? So we can example M parallel maybe and M perpendicular, which parallel to our prime. So M perpendicular are mutually perpendicular. They can be erased as go forth R acting at another point O prime, right? And uh, O prime. There is another point. It's another one. So that's very generalized condition. We will the force is to know we get better friend. The principal moment FO. Maybe this page do a further explanation of when MO perpendicular to R prime. We can use R X on the O prime, right? I think I just explained that to you guys, right? We can find another point O prime, just like the original MO will be counterbalanced by another one, right? So I will do not repeat that again. Maybe that a little bit difficult for you guys to totally understand. So that is not our main point. You guys only need to have a basic knowledge, a basic impression is enough. We just move on, right? And so we'll talk about the very important thing for us, the equilibrium equations of a force system in place, in plane or in space, and their applications. Actually, we can say that any force system is what? I cannot open my video too, right? I don't have that menu. Maybe you guys cannot see me, right? I don't know why. Anyway, I just continue my lecture today. So we talk about the equilibrium equations of a force system and their application. So actually, we have to talk about the first situation. If when we finish our reduction, we find under this R prime, equal 0 vector, and MO also equal 0 vector, right? That means principal vector R prime equal 0, principal couple or moment, principal moment MO equal 0. So that means the absolute value or magnitude of R prime and MO also should be 0. This is just according to the mathematical point, mathematical knowledge, right? Because R prime and MO are both vector, have 3 components, right? So the equilibrium equations of a force system in space, in space, they can also be expressed by what? So this is because this is the vector equation, we can do projection this equation onto 3 axes. So we have sigma x equals 0, sigma y equals 0, sigma z equals 0. So maybe I will further explain to us. So if we see actually R prime is the vector, it will have Rx, I, plus Y, G, and RZ, K. If this is on the condition of equilibrium, it means it's 0. It's 0. So that means it's Rx, which equal sigma Fx. So maybe we write like this, sigma S. So someone tell me something. I cannot find the manual. So maybe you guys can just tell me through the WeChat group. I don't know why. It's very weird, right? What's happening? So can you guys just tell me from the WeChat group? I cannot see the list. So you can see when I move my mouse here, it cannot show me the menu. So I can select to see the list, to check your attendance and to do another things, right? So which one is give me the what? Give me the message. I cannot look at that. Maybe you can just talk to me, okay? So, or maybe I will just continue. So this means, I am I normal? Can you guys still hear me and see the screen?
Yes.
Yes.
OK， 那么我们就继续了 OK。So that's why when we talk about R prime equals 0, we have 3 equations, right? Because Rx actually equal sigma Fx or sigma x and sigma y, sigma z. So maybe I think this symbol should be read as sigma, right? But in many cases, we also call that sigma. It's a lot of atoms sum, right? And this, because MO is a vector 2, it will have 3 components along X, Y, and Z. So if this one is 0 vector, then its 3 component also should be 0. So that means if the force system is in condition in equilibrium, so we can use these 6 equations to find some unknowns, right? They can also be expressed by such as 4 moment equations, 5 moment equations, or 6 moment equations. It don't necessarily not that important. You only need this to remember this is enough, right? And the equilibrium equation of a concurrent force system in space. You see, the equilibrium equations of a concurrent force system in space will only three. Why? Why we do not need to consider these three? Because all action lines of the forces are concurrent at a point, and all axes are through this point. The moment equations are identities, right? So this means always be zero. It always be true. So when you try to give an equation like this, maybe you will get a result like this. 0 equals 0, or 5 equals 5. You see, it is an equation, but it has no use to help us to find some unknowns. Actually, do you guys still remember we have talked about, when we talk about a force, maybe a force F to an axis F. So if this, we have two categories. One is maybe I can just draw a arbitrary axis, maybe X. If this force F is action line, is parallel to this axis, then we will have mx f will equal 0. Another thing is if this action line of f will cross with this axis, then this time mxf also equals 0. Why? Because we can find the result from the definition of moment of a force to an axis. So when we talk about the moment of a force to a given axis, right? First, we should find a plane which is perpendicular to the axis x, right? And have an intersect point O, right? So when we talk about the moment of this force in space to this axis x, just need to projection onto this plane. So we get a projection force F, X, Y maybe, right? So maybe just use M prime. So you can see actually this moment of force F to this axis will equal moment F MO from F prime. And F prime is the projection force of this force F or this force F. So when the first category, the F is parallel to X, so you guys can think about that. Its projection force F prime will be 0. So its moment to point O will be 0. So the moment of this F to this axis will be 0. The second category, if this action line of F will have cross point with this axis, although its projection force F prime will not 0, but it will through the point O. So this case, it also be 0 because this one will equal F prime times H. But H will be 0 because this projection force will through the point O. Right? That's why we call that all action lines of the forces are concurrent at a point, and all axes are through this point. So all the force of this concurrent force system will have 0 moment to the 3 axes x, y, and z respectively. So all these equations will be identity. Identity in Chinese we call that 恒等式. 恒等式 means 永远成立. Always be true, right? But it will have no help to us to find some unknowns. Maybe a given force have unknown direction and unknown magnitude. We try to use some equation to find its unknowns, right? But these 3 equations cannot be used. If you use that anyway, you will find like this. It have no any help to you. So they tell us the equilibrium equations of concurrent force system in space. That's only 3 equations. So if I change this precondition into the equilibrium equations of a concurrent force in plane, right? If it is in plane a concurrent force system, then this one will be another identity, which is always be true. So our equation is only 2, right? So actually this one will be used, we will use that, right? So let's continue. The equilibrium equations of a parallel force system. So the equilibrium equations of a parallel force system in space, supposing all the action lines are parallel to axis Z. So maybe if we give a picture here, it do not give, so I can draw for you guys. So if we have a parallel force, we have F1 maybe, F second, and F a lot of force, but they always parallel one to each other. Like we have this coordinate system X, Y, O, and Z. That means all the forces are parallel one to each other, and all the forces will perpendicular to the plane X or Y, right? So this is the kind of force system. We call that a parallel force system. In space, in Chinese, we call that 空间平行力系, you know, 空间平行力系. So supposing all the action lines are parallel to axis Z, just like this picture, you see? So its equilibrium equation will only these 3. So the first one is sigma Z equals 0. Actually, this one equals all sigma Fiz, right? Equal 0. You know, so actually we can predict all the forces because each force is parallel to z-axis, but some along positive direction of z and some along negative direction of z. So their sum should be equal 0 if it's in condition of equilibrium. So this one is the equation. Another is all these forces is moment to x-axis and the y-axis should be 0. So all these 3 will be its equilibrium equations. And you guys can see that the left 3, the first one, sigma mzf means all the forces is moment to axis z. You see, we have 3 short lines, means this is identities 2, 恒等式. You see, all the forces in action line are parallel to the axis. Of course, the moment to the axis will be 0. How many numbers of this kind of force? All the moment to axis they will always be 0. So this is identity always be true, have no any helpful to us to find unknowns, right? And because our forces are perpendicular to this plane x or y, then when we do projection, all the components of the forces along x-axis and y-axis will always be 0. So you just need have a lot of 0, sum of 0, right? A lot of sum of 0. So it always be true. So these 3 equations will have no help for us to find some unknowns. So we see that the equations of a parallel force system in space only have 3 equations. So once again, if we have a parallel force system in space, change into in plane, we will only have what? We will only have 2 equations, right? 2 equations. If all these forces have to be in the plane y, o, z, right? Then all the action line will cross to axis y. Then this one will be changed into identity. So if a parallel force system in plane, it only have 2 equations, right? So let's move on. And the equilibrium equations have a general coplanar force system. That's our main focus. 平行力，平面力系 right? 平面力系 So if forces acting on the body, the lines of action of these forces are in the same plane, which called coplanar force system. Then its equation will only 3, right? So you see, coplanar force system can further subdivided into 3 categories. One is the coplanar system of concurrent forces. So you can just compare to a force system in space. So this means coplanar system of concurrent force system. We call that 平面汇交力系。Then its equilibrium condition only will be sigma x equals 0 and sigma y equals 0. Right? So I can draw a 平面汇交力系 for you guys. So we have like this F1, F2, and F3, a lot of things. But it on the same plane, just like this white plane. So you see, it always will have a resultant force Fr. It will equal Fi. Because this vector is in the plane, so it only has 2 components. One is Frx along x direction, another is Fry along y direction. It always have 0 component along k direction. We see this coplanar system of current force system in equilibrium, then this one should be 0. So we have actually this sigma x equals 0, e Rx equals 0. Sigma y equals 0 is this Fry equals 0. So this is 平面汇交力系. Another subcategory of coplanar force system is coplanar system of parallel forces. We call that 平面平行力系. Right? So maybe I can draw a 平面平行力系 for you guys. This is our default coordinate system, x or y. Maybe we have like F1 and F2 and F3. A lot of, but all the action line of these forces are parallel to y-axis. So its equilibrium equation will only be sigma y equals 0 and what? And sigma MOF equals 0. So because all the forces in the same plane will perpendicular to the x-axis. So when we write like this, sigma x equals 0 will always be true. So it is another identity. So 平面平行力系 will only have two equations. So general coplanar force system, we call that 平面一般力系. So we can think about actually 平面一般力系 equivalent to a 平面硅胶力系 plus a 平面平行力系, right? So to a general coplanar force system, set the plane of action of forces in XOY plane, right? So the most important three equations I need you guys to understand and to know that is this. Not this one, actually we always draw like this. Our very important three equations is sigma x equals 0, sigma y equals 0, and we can arbitrarily select the point and all the forces its moment to the point O is there is sum will be 0. So this is very, very important. We will use a lot of examples to show you guys how we use this three equation to find some unknowns, right? So actually this is the general coplanar force system. It's three equilibrium equations. Of course, we can write it like this. Actually, it's equivalent. But this 3-1 is very easy to understand why. So we can recall what we have said. A free body in a plane. So if it is a free body, we call that a body A. It can move freely along X or Y, and it can rotate around an axis which is perpendicular to this plane. So it has three kinds of freedom. But if we set it in equilibrium condition, so it will in a stationary state or keep its original state, maybe just move along a straight line, right? So this time will tell us this, sigma x equals 0, sigma y equals 0, and whichever point we select, all the forces acting on this object, its moment sum will be 0, right? So actually this 3-1 is very, very important. So this is one. So when we write like this, it tells us in plane, maybe I draw again, because our default always be like this, y and z. So you know actually from right-hand rule, our z-axis will always be perpendicular to this plane, right? So if this object under some generalized coplanar force system and in the condition of equilibrium, that means any point on this plane we can select, we can write as MAF equals 0, right? But actually, our z-axis will always perpendicular to this plane. So this is the same, right? This is the same. So actually, this means actually this O can be any other point on the plane. Why? Because this x or y just a reference coordinate. It is the aided coordinates just selected or built by ourselves. We can select any point we like to build this coordinate system without changing the state of the object, right? Actually, the object state is independent to our reference coordinate. So it will be very weird if we say at different reference coordinate system. This object will in different condition, maybe balanced, maybe not balanced. It's not true. right? So that's the very simple one. Actually, all things you guys should know and understand in this 3-1, right? In this 3-1. And so if you can understand general coplanar system, so actually the equilibrium equations of a coplanar system of concurrent forces, we can look at this as a special平面一般理系 right？ 特殊的平面一般理系。That means this concurrent forces, when we because this one will be always true is identity, always have three short lines. Why? Because all the lines are intersect into same point, right? So if we select this O, we can find out the out forces is moment to this point O will be 0, right? And maybe someone will ask me a question. Sir, although all the forces are intersect at this O, but if we try to consider as moment to another point like O prime, you see, actually this concurrent force system is reluctant force will be R prime, right? And its reluctant force R prime is independent to the position you select. In other words, if you select O prime, I always can get the same magnitude and direction of R prime. You see? So this one will always equivalent to this one. It's the same, right? So if a concurrent force system, coplanar system of concurrent forces in equilibrium, it only means R prime equals 0. So it will have two components. This one equals 0 and this one equals 0. And others have no meanings or is meaningless. And once again, the equilibrium equations of a coplanar system of a parallel force system. It also can be looked at another kind of special general coplanar system of force system, right? We only have this, right? I think this 2-1 is very easy to understand. Actually, when we encounter maybe coplanar system of concurrent force system, of coplanar system of parallel forces, we can just look at it as a general force system on the same plane, right? Maybe we just have like 0 equals 0 identities, but it's okay. We can find the unknowns anyway, right? So we still have some time. Maybe we can look at some examples after this. And couples in space and couples in plane. So if we if we have R prime equals 0, right? Do you remember? And M equals some value not equal 0. So this means this one will have 3 components. One is this and this. But if it tells us this couple system is equilibrium, that means this one is equal 0. So its 3 components should be 0. So you guys just have impression enough. It's not important to us. And the couple in the same plane will only have one equations, right? Because these two ones, we can look at couples in the same plane as a special case of couples in space, because this one and this one change into identities, 恒等式 always be true, right? So it only have one equation left. So we talk a lot of things. So we can do a very short summary. So I will draw a ticket and tell you guys which one you should understand and remember, right? So a general force system in space, actually, it will have 6 equations, equilibrium conditions, the 3-1 and this 3-1. And the general coplanar force system will have these 3 equations. This is very important. We should remember that. That is sigma x equals 0, sigma y equals 0, and an arbitrary point select all the forces in the system. Its moment sum to this point O will also be 0. Right? So this is very important. And concurrent force system in space, it will means because it will means r prime equal 0, right? Because MO always 0. So it means 3 equations. You just need to understand it a little bit more is enough. But coplanar system of concurrent force system is very important because it's just another special case of a general coplanar force system. This time we only have 2 equations. One sigma x equals 0, another is sigma y equals 0, right? And parallel force system in space, we have 3 equations. This one and this one and this one. You guys only need to have the basic impression is enough. But once again, coplanar system of parallel forces is also another special case of general coplanar force system again. So this one you also need to pay attention to. We need to know it will have 2 equations. Along some direction, its sum of the force will be 0, right? Actually, this direction will parallel to the direction of the action line of the forces. And we can arbitrarily select the point. Our force is moment sum to this point O will be 0. See, the right part is important. The left part, you guys only need to have a basic impression, right? Let's finish the discussion of the principle of prime and the principal moment MO. And then we talk about the equilibrium condition, the equilibrium equations of the different cases, right? The right one is the important part, right? These 3 is very important. And we talk about some application. Maybe you guys just need to listen to me. Maybe next time we through some examples, you will know. So we have 2 concepts. One is statically determined, you know, how to understand statically. Am I right? I think it's hard for me to read it. Statically determined. In Chinese, we call that 静定问题. 静 statically, 定 determined means 确定, 决定, right? So we call that statically determinate problems and statically indeterminate problem. We call that, because this is a negative prefix, we call that 静不定问题. How should we understand these 2 concepts? So let me introduce this concept to you guys. So to a general coplanar, coplanar force system, 平面力学, 平面力学 only consider about 3 equilibrium conditions, right? So to a general coplanar force system, there are three independent equations which can determine three unknown quantities. Can you guys understand that? So from the equilibrium condition of a general coplanar force system, we know that there are only three independent equations which can determine three unknown quantities. So according to this, when the number of equations greater or equal to the number of unknown quantities, we call that this kind of problem is a statistically determined problem, because which can be solved, right? Because the number of equations greater than or equal to the number of unknown quantities, right? The second, when the number of equations less than the number of unknown quantities, we call it is a statistically indeterminate problem. So I will give you guys a simple example. You see, these three equations can help us to find the three unknown quantities, right? Let's see. Let's see a very a simple example. You see, we have a beam. We call that a beam, right? A beam. In Chinese, call that liang, right? So there is the active force P along this direction acting on this point. And there are two constraints at A and B. So we know that at A, it is a fixed support. Am I right? So we know a fixed support, it will have two reactions. One is XA along positive direction of X axis. Another is YA along positive direction of Y axis. And this is roller contact or roller support. Roller support. That means it's along this beam. It can move along X direction, but it cannot move along Y direction. That's why we have a reaction YB along this vertical direction. See? So if this P is magnitude and direction is known, we know that is known, right? So we can find that actually because we have what? Because we have three equations. So we can use sigma x equals 0 and sigma y equals 0, or maybe sigma MAF equals 0 to find unknown x, ya, xa, and yb. See, that is the so-called statistically determined problem, right? Statistically determined problem, right? And let's see the right one. You see, this time we change this constraint into another fixed support. Then, according its reaction, we will have YAXA, YBXB. So the unknown quantity is 4, but we only have 3 equations. You see? So our equations number is less than 4. So this is so-called what? Statistically indeterminate problem. But you can find from our I think experience of life, this beam will be very balanced compared to this one, right? But how to find out the 4 unknowns? So maybe we will wait until next semester. We will learn another course. Its name is Engineering Mechanics Second. We can write at EM2. This semester, I'm learning Engineering Mechanics 1 with you guys together, right? At that time, next semester, we will talk about the deformation of a part under some forces. Then we can give a compulsory equation. So this kind of problem maybe can be solved, but not today, not this semester, right? And statically indeterminate problems can be solved by the conditions on compatibility. Compatibility, 协调条件. That means we should add another actual equations, you know? So I think that's all for today. Although we still have 3 minutes to finish, but this is our homework today, right? You guys, this is our homework today. So please, you guys, you can find it a written position from our textbook, and you can try your best to finish. Just use 3 equations: sigma x equals 0, sigma y equals 0, and sigma m some point, maybe MAF equals 0, to find reaction of XA and YA and YB, right? So this is homework for you guys. I hope you guys can finish by yourself. And the next time we will talk about this problem first, then we'll move on to the new constant. Next time we'll do a lot of examples. We will use these 3 equations many times, right? I think that's all for today. Bye bye, you guys. 下课吧，再见。
OK，老师。
好的，
再见，老师。
再见。
OK，老师，再见。
Bye bye. I don't know how to close this Tencent session because I don't have the manual. It's so weird.
Thank you, Lao Shi.
Bye bye. Bye bye.